Hi everyone. In this video, we're going to look at some of the characteristics of quadratic functions. So quadratic functions, well, quadratic means that we have degree 2 functions. We have a function. There are quadratic relations. We'll look at a tiny bit with quadratic relations in this course, but mostly we're going to focus on functions of degree 2. So the simplest one that we can look at is the one that you can see here on the screen. Y equals x squared. It is a function. It is degree 2. There's really not much else to it. But we can see when we graph this that what we end up with is this curved shape. This shape is called a parabola. Now, this parabola has a number of characteristics. First off, we have a vertex. And in this case, the vertex is at the point 0, 0. So that's sort of the baseline starting point for a vertex. And the more complicated our equations get, the vertex is going to move around, but this same basic shape is going to exist. We're going to have a vertex, and we're going to have this same curve shape called a parabola. The parabola is symmetric around a vertical line through the vertex. Now, it is possible to turn my parabola around so that this line of symmetry, and we're going to call it the axis of symmetry, is not a vertical line. But if the axis of symmetry is not a vertical line, then the parabola isn't a function. So if I sketch, for example, a parabola that looks like this, where the vertex is there and the axis of symmetry is some sort of diagonal line, we can see pretty quickly that that is not going to be a function because a given x value will have more than one y value. So if I want to keep it as a function, and we do for this course mostly, my axis of symmetry is going to be a vertical line, so it's going to have the equation x equals something. And since it is through the vertex, it is x equals 0, because that is the x value of the vertex, and that's in fact the x value of every single point on this line of symmetry. The symmetry means that for every point on one side of the vertex, there's a corresponding point on the other. So for example, if x equals 2, then y equals 4, because 2 squared. So I have a point here at 2, 4. But I have a corresponding point over on the other side at negative 2, 4. So same y value for two different x values. And those x values, positive and negative 2, are the same distance away from the axis of symmetry. The domain of every one of these quadratic functions is going to be all real numbers. Now, we may have some contextual problems where our domain is limited by real life limitations, but the mathematical limitations, there aren't any. I can always square a positive number or a negative number or a fraction or a decimal, or it makes no difference. There's no limit on what sorts of inputs I can have in this function. Any number can be squared and give an answer. However, for the range, there is a limit because in this case, if I'm squaring a number, my result will always be greater than or equal to 0. So the range actually belongs to the interval of values that are from 0 to infinity. So those are my domain and range here. Now again, those will shift a little bit as we do various changes and get some slightly more complicated looking equations, but the basic principles are the same. In this case, my vertex represents a minimum point of the parabola. It is possible to have that vertex be a maximum. We'll see some examples of that in a moment, but the vertex is the lowest point of this parabola. And so the y value of the vertex, the 0, is the minimum of value of y that I can have in this function. All right, so that's the basic thing. We'll have domain range questions. We'll look for our axis of symmetry in our vertex. We'll consider whether we have a minimum or maximum as we get more complicated equations. So let's jump right into one. We've got here a function y equals 2 times x plus 3 squared minus 8. So we can still see its degree 2, and we can still see that basic shape of a parabola. We have a vertex at negative 3, negative 8. We have some x-intercepts here. Our x-intercepts are at negative 1, 0 and negative 5, 0. And we have a y-intercept of 0, 10. Now, if I think about domain, the domain of this function is still going to be all real numbers. Because think about what this equation is asking me to do. I take an input, I add 3 to it. Well, it doesn't matter what input I start with. I can always add 3 to any number. Then I square it. Cool, I can always do that. Then I multiply it by 2. No restrictions on that. Then I subtract 8. Well, all of those operations can be done with any real number. So my domain is all real numbers. From the graph, however, I can see that the minimum point is the vertex. And therefore, my minimum y value is negative 8. So y has to belong to the interval where -8 is the lower limit. There is no upper limit. It goes up to infinity and potentially beyond. Not drawn here are the arrowheads, but we do understand that this continues on and on forever. Now, if I reason my way through this, if I didn't have the graph, I could still come to that same conclusion that the minimum value of y has to be -8. Again, by thinking through, what do I do with the inputs into this function? So I take an input. My input can be any real number. Then I add 3 to it. Well, adding 3 doesn't really introduce limitations. If I could start with any real number and then add 3 to it, I can still get any real number. Now I square it. Well, when I square it, now it has to be greater than or equal to 0. All right. Multiply by 2. Multiply by 2 doesn't change that. It still has to be greater than or equal to 0. If I started with a positive number, I'm going to still now have a positive number. If I started with 0, I'm still now going to have 0. But when I subtract 8, that minimum of 0 now moves down to -8. So looking at the graph, I can see that. But also thinking of the equation, given that this whole squared part right here, 2 times x plus 3 squared, has a minimum of 0, when I then subtract 8, I now have a minimum of -8. Looking at the vertex, so we're going to compare the vertex with our equation. So remember, the vertex, we can see over here on the graph, is at the point -3, -8. I've already sort of explained how we can use that equation to reason out why -8 has to be the y value of the vertex, but it isn't an accident that this bit right here corresponds to the -8 in the coordinates of the vertex. It also isn't a coincidence that there is a relationship between the first operation I have to do to my input, so the x plus 3, and the -3 I have in my x value of the vertex. So essentially, because I started out with a vertex at 0, 0. Now, this explanation isn't going to be fully comfortable right this moment. We are going to continue to discuss these sorts of things, these ideas of what are called transformations, over this semester and, in fact, next semester. So don't worry too much if you're not completely comfortable with this explanation immediately. We will keep coming back to it. But essentially, because I was at a starting place of a vertex of 0, 0, I'm now saying I need to be able to put in some new x value, but still have an output of 0 before I square it. Because my original function, y equals x squared, the original operation was just to square the input. So if I'm saying, well, I need to be able to put in some new number and then do some operation to it before I square it, that would get me back to 0. So if that operation that I'm doing is plus 3, what number would I have to put in there to get a 0? That's essentially the question that's being asked. So if I look at this equation and I look in the brackets and see x plus 3, I know that I need to put a -3 in there to get 0. So the vertex has to be at an x value of -3. The vertex being at an x value of -3 also means that my axis of symmetry is the line x equals -3. And if I look at my x-intercepts, I can see, because remember we talked about symmetry before, these x-intercepts are on either side of that axis of symmetry, and they are the same distance from it. So -3 minus 2 would give me the -5, and -3 plus 2 would give me the -1. So actually, once I find one of my x-intercepts, I can find the other. We're going to spend a great deal of time talking about how to figure out those x-intercepts. It's not immediately obvious from this equation, but there are some manipulations we can do. But the symmetry part is the critical part. Moving on now to a couple of different forms of equations. This is also a quadratic. Y equals -1/3 times x plus 1 times x minus 7. I know it is quadratic because if I were to distribute it, x plus 1 times x minus 7 gives me a quadratic. So I've got two factors essentially. That would give me x squared minus 6x minus 7. But then, of course, still times the -1/3, which is going to leave me with fractions. So if I were to distribute this, I can see very clearly that it is, in fact, a quadratic equation. It's not in the same form as what we had in the previous example, though. So my vertex isn't quite as obvious. And again, we're going to spend time algebraically figuring out how to figure out the vertex. But from this graph, I can see the vertex is at the point 3 and then 5.3333, so 5 1/3, or if you want to think about it as 16/3, that works too. So the vertex, which in this case is now a maximum. The thing in the equation that indicates to me this is going to be a maximum is the fact that when I square, so thinking of inputs, if I square this input, I end up with a positive number, but as soon as I multiply it by -1/3, I end up with a negative number. So values are going to actually now start going down. It's a little more complicated in terms of this calculation because my input shows up in two places, x squared and x. But it's the x squared term that really determines because it's the bigger term. So if I have a negative there, when I square that number, I'm going to get a positive. The 2x, that could be positive, that could be negative, depending on whether x was positive or negative to begin with. But the -1/3 x squared always, 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 always has to be negative. So in other words, I end up with something that's less than or equal to 0, but then it moves around. And so in this case, my range actually ends up being y is less than or equal to the 5.333, which I'm going to call 16/3, that I can see on my graph. So y is less than or equal to the vertex. That 16/3 value is not immediately obvious in this equation. That's okay. I'll get to that in a second. But on the graph, I can see where it is. So let's put this in some proper notation. My range is y such that y is less than or equal to 16/3, and other than that, y is any real number. Domain, as always, x is an element of the real numbers. There's no mathematical limits on domains that show up in quadratic functions, even though there might be contextual ones. Now, from my graph again, I can see where the vertex is, so I can see that the axis of symmetry is at x equals 3. But I don't really see that in the equation. So when the equation is either distributed or in factored form like this, the vertex isn't as obvious as when it was in this other form. This form is actually called, logically enough, vertex form, because we can easily see the vertex. This form that we're dealing with here, you're familiar with from Math 10, this is factored form. Now, what I can see very easily in factored form are the x-intercepts. So consider here that my x-intercepts are -1 and 7. These relate to my factors in that these are the values of x that turn my factors into 0. -1 plus 1 would give me 0, and then 0 times whatever else I have in that equation is going to be 0. That's why y equals 0 there. And 7 minus 7 gives me 0, which would then also give me 0 for the whole function. So when I have factored form, I can easily see the x-intercepts. The x-intercepts, remember from our previous example, have to be the same distance from the axis of symmetry. So if I can tell that my x-intercepts are 8 units apart, which I can because -1 and 7 are 8 units apart, then halfway between them must be the axis of symmetry. So the average of those x-intercepts, -1 plus 7 divided by 2 is 3. That's where the axis of symmetry is found. So actually, that's how I could have found also the 16/3 that I needed for my range. Because once I know that the axis of symmetry is when x equals 3, I know that the vertex happens at x equals 3. So then I can simply substitute in y equals -1/3 times 3 plus 1 times 3 minus 7. So this is for the vertex. And when I do that calculation, I get 16/3. So if it wasn't obvious on my graph, but from factored form I can figure out the x-intercepts, that is how I can figure out where the vertex is. And just recalling, because I have this negative value here, that's why the parabola is now opening downwards instead of opening up. It still has symmetry, it still has all real numbers, it's just now my range is going to be less than or equal to something instead of greater than or equal to. All right, well, what if I have a parabola in distributed form like this? It's not in factored form and it's not in that vertex form. Well, if I can factor it, then I can do what I was dealing with in the first example. And this case actually is factorable. So we can factor this and it becomes, first thing to note, the 2 here is positive. So because the 2 is positive, this parabola is opening upwards and I'm going to have a vertex which is a minimum instead of a maximum. In this previous case, my vertex was a max, as we saw. All right, so the factors here, we end up with 2x minus 5 and x plus 1 as our factors. So when we look at the x-intercepts, we can actually see exactly why that would be. So 2.5, if I plugged in here, 2 times 2.5 is 5. minus 5 would give me 0. And, oops, that should be a minus 1, not a plus 1. Then if I substituted in 1, which is my other x-intercept, 1 minus 1 would also give me 0. So those are my two x-intercepts. My axis of symmetry, therefore, has to be exactly halfway between them. Now, I can see on this graph where the axis of symmetry is, but if from that factored form, I just know I have 2.5 and 1, I can average those two numbers. So 3.5 plus 1, or 3.5, sorry, divided by 2 is 1.75. So that is the x value of the vertex. It is also the equation of the axis of symmetry is x equals 1.75. Or you could have that in fraction form if you wanted. That is 7/4. All right, so how would I then go about finding this y value? We can just plug it into the original equation. Not going to bother doing that here because I actually have it on the graph, but I would take that 7/4 and I would do 2 times 7/4 squared minus 7 times 7/4 plus 5, and I could get the y value. But here I can very easily see what the y value is. So I can figure out that my domain is all real numbers. My range is y such that y is greater than or equal to negative 1.125, and otherwise y is an element of the reals.